Okay, AP Bio fans, here we go again. Chapter 3 in water. Of these two chapters, chemistry and water, that we are working on in this section of the unit, probably the water chapter, I shouldn't say it this way. Chemistry is very important, but not, but in contextual stuff, you've had chemistry as a background or concurrently learning it, and that is fine. Water is where you'll have less experience. And water has introduces a concept to us called emerging properties, which is the idea that as you increase in levels of complexity, so for example, water is just hydrogen and oxygen, okay, bonded together. The properties of hydrogen and the properties of oxygen are nowhere near the properties of water. By coming together, you get what are called emerging properties. Hydrogen and oxygen themselves, while important, are not as important as the properties that emerge from water that make it absolutely life-sustaining for us carbon life forms. Okay, so let's talk about water. It is the molecule that supports all life. Water is the biological medium on Earth. All living organisms require water more than any other substance. Most cells are surrounded by water, and cells themselves are anywhere from 70 to 95% water. And the abundance of water on the Earth is the main reason it is habitable, at least for now. Okay. Water, as we saw in our little chemistry quick review, is a polar covalent compound. Okay. Polar because that draw of the oxygen, the highly electronegative oxygen, on the not so electronegative hydrogen, or not as, pulls the hydrogen electron more into the oxygen sphere, creating that dipole moment and that slight charge. That polarity, then, as we saw, allows weak hydrogen bonds to form with each other. There we go. We saw that in our chemistry unit. Okay. The hydrogen bonds in liquid water last only for a few trains of a second, but as soon as they break, they reform with a succession of partners, so water is actually more structured than most liquids. This gives rise to some properties sometimes called emergent properties. And again, yes, you have this dipole moment here, but that can break and reform with another water molecule nearby. Break and reform, break and reform, break and reform. But it's happening so rapidly, it gives it structure. What are our emerging properties? The ability to moderate temperature. Okay. You would have learned in chemistry that no substance absorbs more energy than water. Okay. That's why it's used as the basis of coolants for most machines, and started that way also. And folks who live along the coast, either east or west, can tell you, especially the West Coast, can tell you how it keeps the temperature moderated. It expands upon freezing, and the density of ice is less than the density of the liquid form and can float. That is the only substance that has that difference. It's cohesive. We'll talk about how do you get water up to the top of the redwoods, that hydrogen bonding pulling, and it's the universal solvent. Why? Because the only non-polar molecules we have are diatomics and carbon-hydrogen bonds. Everything else is polar, whether it's an ionic bond or a polar covalent bond. Now, they all have different degrees of which they will dissolve, and part of that is, not very polar substances really don't dissolve well in water. They really need a non-polar substance, but that's only because they are not very polar at all and closer to the non-polar covalent era. Okay, so little reminders about heat. Total measure of kinetic energy: molecules move faster. That's an increase in temperature, which is the average kinetic energy of speed of the molecule. Why does the metal pan heat up faster than water? Because the water can absorb. Because of those hydrogen bonds and the breaking and reforming and everything else, it can absorb much more heat. High specific heat, 1 calorie per gram per degree centigrade. Okay? And remember, the specific heat is the amount of energy needed to change 1 gram by 1 degree Celsius. That is up there with the highest that are out there. Okay? Which also stabilizes the temperature on our planet. Besides stabilizing the temperature of living organisms, like you always hang around 98.6-ish, 37 degrees Celsius, it also stabilizes the planet as a whole. Okay? Remember, heat of vaporization, the quantity of heat that must be absorbed for a gram of substance to go from liquid to gas. High heat of vaporization, so it takes a lot of heat to convert it to a gas. That's good for you, me, and other living things. Otherwise, the transpiration of water into the atmosphere would go rapidly. Who knows? Evaporation, crazy. Okay. So what's evaporative cooling? You may not have talked about this in chemistry. It certainly is in the application in a biological sense. Since the highest energy molecules are popping off, those left below have lower kinetic energy, so the temperature decreases, so it has a cooling effect. This is again why you don't look in the crock pot. But why, as you sweat and you wick away the sweat from your body, do you feel cooler? It's evaporative cooling. Okay. There's an example. You can see the Pacific Ocean and the California coastline. And honestly, everywhere from San Francisco through Los Angeles through San Diego, their temperature's relatively stable. I mean, certainly there's fluctuations, but honestly, relatively stable because of the water. Now, you don't go that far in. You go to Burbank, San Bernardino, Palm Springs. You've got the desert areas. They're not near the water. That sun bakes and their temperature goes up. Right? And if you think of all the water covering the earth, the stability that gives to our earth. Okay. And if you remember a heating curve from chemistry for energy, remember that area of 0 degrees Celsius when you're freezing to 100 degrees Celsius boiling, that's a huge range and a lot of energy that can be absorbed. Okay. Right? So there's the big range of solid, liquid, gas. If you keep cooling down water, you know that old rule, heat expands, cold contracts, only to a point for water. At about 4 degrees Celsius, then the lack of kinetic energy results in the ability to break bonds, so the hydrogen bonds lock into crystalline structure, freeze, and have a lower density than liquid water, ice floats. Okay? Add heat, increase the kinetic energy, disrupt the hydrogen bonds, and it melts. You break those bonds, the molecules start separating away. Okay? All right. And expands upon freezing. Ice floats in liquid water because hydrogen bonds on ice are more ordered, making ice less dense. Water reaches its greatest density at 4 degrees. If ice sank, all the bodies of the water would eventually freeze solid, making life impossible. Think of all those little fishies and critters and things that are living below the ice and a relatively stable temperature below the ice. And what would happen if the ice sunk and froze from the bottom up? That's an emerging property. Cohesion of the water molecules. Collectively, hydrogen bonds hold water molecules together, called cohesion. Helps transport of water against gravity in plants. Adhesion, why you see the meniscus in a graduated cylinder, and remember, it graduated because it passed my class. Adhesion is an attraction between different substances, for example, the plant, between the water and the plant cell walls. So it's pulling up, okay? So how do you get water from here up to the top of the tree? How do you pull it up? Well, one, two things really, and there's no animation here. As you open what are called stomata on the leaves, and it releases water, gases, whatever, and the water vapor and transpires out of there. The molecules that are below in the veins of the plant, because they're bonded together, because of those hydrogen bonds, will pull them up. And also, what helps pull them up, and this is how you get to the top of the redwoods, you've seen that meniscus in the graduated cylinder, that's the adhesion to the sides. So between sticking to the sides and getting pulled up from the water that's leaving at the top. And so the next ones are getting yanked up. There's a pressure dynamic in there. But that allows you to get the water up to the top of the tree, adhering to the sides of the plant wall as it pulls up the veins. And then, of course, you create a pressure differential that pulls up water, and every water molecule is attached with hydrogen bonds, so it keeps pulling all the others up. Okay. And you can see here's the adhesion to the side of the walls. Here's the cohesion of the molecules. And because of opening of the stomata up here, it pulls everything up. Okay. Transpiration and pulling up a tree, water attracted things like the meniscus. Maybe I'll find a different way and connect this link here. There's a great surface tension moment. Okay. That is another emerging property. And I will pull that up and put that on the website and you can watch that. Okay. Surface tension is a measure of how hard it is to break the surface of a liquid. Surface tension is similar to cohesion, the molecules, and it's why little buggies can run across the top of the water. Okay. So I'm making a note to show that little short surface tension film and put it on our Schoology site. Okay. And then here's some chemistry. Water is a solvent of life. Remember, a solution is a liquid that is a homogeneous mixture. The solvent is the dissolving agent, 99% of the time water. Well, I shouldn't give it a percentage, but I did. The solute is a substance getting dissolved in an aqueous solution, as one is which water is the solvent. Okay. So water is a versatile solvent due to its polarity, which allows it to form hydrogen bonds easily. When an ionic compound is dissolved in water, each ion is surrounded by a sphere of water called a hydration shell, keeping them separated. Water can also dissolve compounds made of non-ionic polar molecules. Even large polar molecules such as proteins can dissolve if they have ionic and polar regions. Okay? Doesn't mean everything dissolves at the same rate or as easily, but it does. There's a hydration sphere around sodium and chlorine. You have an activity that's going to help you understand that. It makes it difficult for them to reform the ionic bond until you evaporate the water. Okay. And remember, hydrophilic substance is one that has an affinity, and hydrophobic is afraid of water. That'll be key for our cell membrane and cell talk. Oil molecules are hydrophobic because they have relatively nonpolar bonds, so they don't mix with water. They form little droplets in there, and a colloid is a stable suspension of fine particles in liquid. Colloids, we can talk about them a little bit, but they're not that important. And then remember molarity, solute concentration in aqueous solutions. Most biochemical reactions occur in water. Chemical reactions depend on collisions of molecules and therefore on the concentration of how many solutes are in the aqueous solution. It's a molarity moment. Okay. So, how do we get life on other planets with water? The remarkable properties of water support life on Earth in many ways. Astrobiologists seeking life on other planets are concentrating their search on planets with water. To date, more than 200 planets have been found outside our solar system. 1 or 2 contain water. Mars has been found to have water. There you go. You see little frozen patches of water. Then remember your acids and bases. A hydrogen atom in a hydrogen bond between 2 water molecules can shift from one to the other. So you can get a hydronium ion or a hydroxide ion. Okay. Water is in a state of dynamic equilibrium in which water molecules dissociate at the same rate which are being formed, which is 1 times 10 to the minus 14th. Though rare, the dissociation has a great effect on organism. Changes in concentrations, hydrogen and hydroxide, can drastically alter the chemistry, okay, because it changes the pH, right? Because hydrogen and hydroxide are equal in pure water, so by adding certain solutes, acids, or bases, you change the hydrogen hydroxide content, that changes pH. For you as a living organism, pH changes can't go very far, or it's very detrimental. Okay. Remember, an acid is any substance that increases the hydrogen ion concentration. A base is anything that reduces. We go with the basic Arrhenius type definition here. That's all we need. Again, the pH scale, water normally separates at 10 to the minus 14th. So each of the hydrogen and hydroxide have a 10 to the minus 7th. So the pH is 7 and neutral. Okay. Acids have pH values less than 7. Bases are higher than 7. Most biological fluids range from 6 to 8. There we go. Okay. And what's a buffer? And some of the stuff, acids and buffers, chemistry folks, you'll learn at the end, but you'll see much more of it as you go at the end of honors chem, but you'll have the knowledge long before you need it. The internal pH of most living cells must remain close to pH 7. Buffers are substances that minimize that change. Remember, 1 times 10 to the minus 14th is very small, so even small changes in hydrogen or hydroxide can change the pH. So a buffer minimizes those changes and kind of absorbs those changes. It's usually an acid-base pair that can buffer it's the acid in its conjugate salt or the base in its conjugate, and they allow, what they do, they buffer, they allow a minimal change in that pH. Of course, it's not infinite. You can overflood it and that's a problem. So that leads to acid rain and acidification of water. Human activities such as burning fossil fuels threaten water quality. Carbon dioxide is the main product. About 25% of human generated carbon dioxide is absorbed by the ocean in its cycle. And we'll talk about cycles, chemical cycles in this unit. Carbon dioxide dissolved in seawater forms carbonic acid. That's acidification. So here's the jet, it's absorbed. Carbon plus the water makes the carbonic acid. The carbonic acid then can separate into hydrogen and the bicarbonate. And that's kicking hydrogens. Now the hydrogen with, say, carbonate, which is the key component of like shells and coral and things like that, will then get picked up to again make the bicarbonate, making things more acidic. The carbonate, where did it come from? The calcium carbonate. Okay. So essentially what you're doing to absorb carbon dioxide coming in and absorb the extra hydrogens that are the pH that's thrown in the water is you're binding them with the carbonate, which is coming from calcium carbonate, which is the basis for coral, shells, etc. As seawater acidifies, hydrogen ions combine with carbonate to produce bicarbonate. Carbonate is required for calcification by many marine organisms, including reef-building corals in the shells of many marine organisms. And now you're removing it. Okay? And you can see what happens going from A to B to C. I believe these pictures are from your text. And what has happened to the ecosystem there. Okay. Burning of fossil fuels is also a major source of sulfur oxides and nitrogen oxides. These combine with water in the air to form strong acids of fall and rain or snow called acid rain. Okay. With a pH lower than 5.2, which is pretty acidic for living organisms. damages life in lakes and streams and changes soil chemistry on the land. Okay. And I'm missing a picture. I apologize. Okay. That I was looking for. I'm missing. I want to show you an acid rain picture. That's from your textbook. Anyhow, there you go. That's the basic waters. The key for water in this whole exam and class are the emerging properties. That it's the universal solvent, that cohesion, adhesion, surface tension that come about, that the ice is, that the density of the solid is less than the density of the liquid, so that ice can float and living things in the oceans can live, and life is possible, and not all water freezes. Okay. What did I leave out? It's a solvent. Surface water. Oh, and the evaporative cooling, the ability to absorb a lot of energy. Okay. That's the main takeaways from that chapter as you read it, and we'll be doing activities with that as we get going through this unit. So, once again, hope you enjoyed another AP Biology moment. Have a great day. We'll talk to you again soon.